The common names of ketones are derived from the naming of two alkyl or aryl groups bonded to the carbonyl group. For any hydrocarbon, if you remove last E by adding Al to that, it will happen methanol. Aldehydes and ketones are generally prepared by oxidation of primary and secondary alcohols. When an aldehyde group is attached to a ring, the suffix carbaldehyde is added after the full name of hydrocarbon. Hello everyone, this is Harshita Bhavasar from Vidhyaashram PU College Temple of Excellence. Today I am going to start new chapter, that is from organic chemistry part, Aldehydes, Ketones and Carboxylic acids. In today's session, we will discuss about introduction part of aldehydes and ketones and nomenclature of aldehydes and ketones, nature of carbonyl group, also preparation of aldehydes and ketones we will see. Aldehyde and ketone are the organic compound containing carbonyl group. Carbonyl group means C double bond O, okay. CO group, that is carbonyl group. Any organic compound which contains the carbonyl group will call it as aldehydes and ketones. But there is a slight difference between aldehydes and ketones even though it is containing carbonyl compound. Aldehyde are the organic compounds in which carbonyl group is attached to the one hydrogen atom and one alkyl or aryl group. Okay. Here one hydrogen atom will be there, one aryl or alkyl group will be there which is connected to carbonyl group in aldehyde. In ketone, one carbonyl group will be there, two aryl or alkyl group will be there. In that, one can be aryl, another can be alkyl also, it may present. Okay, see here, this is carboxylic acid. One side OH group will be there, another side aryl or alkyl group and attached to the carbonyl group. This is about aldehydes and ketones and carboxylic acid, but we will study now as per now about aldehydes and ketones. Carbonyl compounds are widespread in plants and animals. There is a n number of important role in plants and animals. They play important role in biochemical process to sustain life. They add fragrance and flavor to nature and constitute several pharmaceuticals. They will be having fragrance, nature also, they will be having flavor, giving nature to the environment through pharmaceutical industries. Some members of these families are manufactured in large quantities for use as solvent and for producing materials like adhesives, paints, fabrics and etc. They will be used as solvents as well as in the production of adhesives, paints and fabrics etc. We will see some of the example. Vanillin from the vanilla beans, salicylaldehyde from meadow sweet and cinnamaldehyde from cinnamon. Okay, this is vanillin and this is salicylaldehyde and this is cinnamaldehyde. And how it has been occurred from through nature. Those things you have to understand. These will be extracted from vanilla beans and this is from meadow sweet and this is from cinnamon which will be used in spices. Okay. This is about introduction of carbonyl group. Next, nomenclature. There are two systems of nomenclature of aldehydes and ketones. First we will see the aldehydes. The common names for aldehydes are derived from the names of corresponding carboxylic acids by replacing oic acid of an acid by word aldehyde. Means it is a corresponding nature of carboxylic acid. So, removing oic acid from carboxylic acid, we will replace that aldehyde group. Branching in the aldehyde chain, if any, is indicated by the Greek letter alpha, beta, gamma, delta, etc. The alpha carbon being the one directly linked to the aldehyde group, beta carbon next and so on. In the group, wherever carbon is attached directly to the carbonyl group, it will be recognized as alpha carbon and next to that alpha carbon will be beta, next gamma and next delta. Like that you have to name. See here CH3, CHO. Okay, this is the aldehyde functional group. So CH3 acetaldehyde in common name. This is benzene, benzene for CHO, that is benzaldehyde. In this example, you may observe that alpha, beta and gamma. Here for normal aliphatic group, CHO is, this is overall aldehyde, okay, CHO group. Here for alpha beta carbon, bromine is added. For bromine, bromo is the prefix word. This is the carbon where it has been directly attached to the carbonyl group. So this carbon will be recognized as alpha and this one beta. So for beta, bromine is added. So beta bromo butyl, because 4 carbon atoms are there, 1, 2, 3 and 4. So 4 carbon atoms are there. So butyl aldehyde. Beta bromo butyl aldehyde. These are the common names. Next for ketones. The common names of ketones are derived from the naming of 2 alkyl or aryl groups bonded to the carbonyl group. I have told CO, R and R dash. It may be 2 alkyl or it may be 2 aryl, or in that one may be alkyl and another will be aryl. In common system, aliphatic ketones are named after the alkyl group attached to the carbonyl group followed by the word ketone. The simplest ketone is CH3COCH3, means it is a acetone. Which is acetone? The positions of the substituents are indicated by the Greek letter alpha, alpha dash, beta, beta dash and so on. Alpha, alpha dash carbons being the one directly attached to the carbonyl group. Okay. Alkyl phenyl ketones are usually named by adding the acyl group prefix called phenone. Okay. One is the functional group of or functional naming of ketone. So here if alkyl phenyl is there, so phenol will be prefix. See here acetone CH3, CO, CH3, this is R and this is R dash. Acetophenone, okay, this is CH3 and this is phenone, that is benzyl acetophenone. This is propophenone because meth eth prop, this is phenyl, so propophenone, and this is benzophenone. One side benzene, another side you can tell as it is phenyl group is attached, so benzophenone will be named. These are all common names. How it will be written in the perspective of aldehydes and ketones. Now we will see the IUPAC naming of aldehydes. The IUPAC naming, aliphatic aldehydes are named by replacing terminal E of parent hydrocarbon by Al. Means if it is alkane is there like methane, you have to remove this E by adding Al, it will happen methanol, means this is aldehyde. For any hydrocarbon, if you remove last E by adding Al to that, it will happen methanol. Al is the which represents aldehyde group. When an aldehyde group is attached to a ring, the suffix carbaldehyde is added after the full name of hydrocarbon. Okay. If any aldehyde group is attached to the ring, that aldehyde will be at the end of the name. In aromatic aldehyde, the functional group may be attached either directly to the ring or may be present in the side chain. In the aromatic aldehyde, the functional group may be added directly to the ring or in the side chain of the ring. The simplest aromatic aldehyde carrying the aldehyde group on a benzene ring is named as benzene carbaldehyde or benzaldehyde. However, the common name benzaldehyde is accepted by IUPAC. Other ring substituted aromatic aldehydes are named as derivative benzaldehydes. See here HCHO, common name formaldehyde or methanol. Only one carbon is present. This is acetaldehyde, this is ethanol, and this is propanaldehyde, meth eth prop, so propanol, and meth eth prop but, Here butyl aldehyde or butanol. Here isobutyl aldehyde or 2-methyl propanol. Okay. It doesn't have common name. 3-methyl cyclohexane carbaldehyde. 3-methyl cyclohexane carbaldehyde. This is cyclohexane structure. For that one side methyl, another side aldehyde is present. And this is alpha methoxy propanaldehyde and this is 2-methoxy propanol. Here valeraldehyde in the common name, but this is pentanol. 1, 2, 3, 4, 5. Acrolein, this is prop-2-enol. This is phthalaaldehyde and benzene 1,2 dicarbonaldehyde. Here M-bromobenzaldehyde, because in the meta group it will bromine is attached. So M-bromobenzaldehyde, this is 3-bromobenzene carbaldehyde, because 1, 2 and 3 at the third position bromine is added. So 3-bromobenzene carbaldehyde. This is how for the group of aldehydes common names and IUPAC name will be given. Now for ketones. In the IUPAC system, ketones are named by the replacing terminal E of the alkene replaced by -one. Same here for methane plus ONE, that is a ketone functional group. This E should be removed and it will form methanone, means that is a ketone functional group. Therefore, saturated aliphatic ketones are called alkanone. The longest carbon chain is numbered to give carbonyl group the lowest possible number. Ketones with carbonyl group attached to a benzene ring are also named as phenone. Some of the names have also been accepted by the IUPAC name. It will be called it as phenones also. Here CH3, CO, CH3, dimethyl ketone or acetone, propanone, because 3 carbon atoms are there. This is methyl and this is ethyl, that is ketone, ethyl methyl ketone, 2 butanone and methyl and N-propyl ketone, 2 pentanone, diethyl ketone, here also ethyl and here also ethyl, so diethyl ketone, 3 pentanone, diisopropyl ketone, see here 2,4 dimethyl pentone 3 none, diacetyl COCH3 COCH3, butane 2,3 dione, and this is methyl oxide, and here 4 methyl pent 3N2-one. This is alpha methyl cyclohexanone. For this carbon is attached, so it will become alpha methyl cyclohexanone. For cyclohexane, one is attached, so cyclohexanone. Here 2-methyl cyclohexanone. Okay, this is how the naming of ketones will be done through IUPAC nomenclature. Next, nature of carbonyl group. Till now you have seen the IUPAC naming of aldehydes and IUPAC naming of ketones also, but both are having carbonyl group. So how the nature of carbonyl bond will be formed? The carbonyl carbon in aldehydes and ketones is sp2 hybridized and forms 3 sigma bonds separated by 120 degree from each other. See here, CO, 3 sigma bonds, 1, 2 and 3. 3 sigma bonds, 1 pi bond will be formed. Those 3 sigma bonds will be separated from 120 degree each other and they are sp2 hybridized. One of the sigma bond is formed with the oxygen atom and the other 2 with carbon and hydrogen atom. One will form with oxygen and other 2 will form with either carbon or hydrogen bond. The fourth valence electron which remains in the unhybridized p orbital overlap with p orbital of oxygen to form sigma bond or pi bond. Okay. The oxygen atom has 2 lone pairs of electrons which occupy its remaining 2 orbitals. The carbonyl group and the 3 atoms bonded to lie in one plane and the electron cloud above and below its plane. See here, oxygen will be having remaining lone pair of electrons and it will form the pi orbital here. Okay, so it will be, there is a presence of electron cloud due to that overall CO group are lying in same plane. So it will be producing electron cloud there and it will form only 1 pi bond and 3 sigma bond. These are all p orbital which is having the electron cloud and perpendicular to the plane of CO group. The carbon oxygen double bond is polarized due to the high electronegativity of oxygen relative to carbon. This is get polarized due to the highly electronegative element which is oxygen. So after polarizing, what will happen? It will get minus sign and it will get positive sign. The electrons, particularly the loosely held pi electron, are pulled strongly towards the oxygen atom and to give oxygen a partial negative charge and carbon as a partial positive charge. So due to its electrons high in oxygen, what will happen? Due to electronegativity high, it will pull the electrons towards the oxygen and it will attain partial minus sign and here partial positive sign towards carbon. Thus the carbonyl group carbon is an electrophilic and carbonyl oxygen as nucleophilic. That's why it will act as electrophilic, which is again act as Lewis acid, and this will be nucleophilic in nature, okay, which is Lewis base. The high polarity of carbonyl group is explained on the basis of resonance involved as a neutral and a dipole structure as shown below. Okay, this is neutral and this is a dipole structure. This is about nature of carbonyl group. Next, preparation of aldehydes and ketones. How? Generally, aldehydes and ketones will be prepared at the same time. Important methods for the preparation of aldehydes and ketones. First type, by oxidation of alcohols. Aldehydes and ketones are generally prepared by oxidation of primary and secondary alcohols. We have told that corresponding group of alcohols are aldehydes. By the oxidation of primary and secondary alcohols, aldehydes and ketones will form respectively. This is primary alcohol. When it is treated with copper at 573 Kelvin, it will form aldehyde. Okay. You can take as example of R, that is CH3 also, CH3, CH2, OH. Same in the copper catalyst, it will form CH3, CHO. Okay, it will form acetaldehyde. By dehydrogenation of alcohols, dehydrogenation means hydrogen atom will be removed by the alcohol, then it will also form aldehydes and ketones. In this method, alcohol vapors are passed over heavy metal catalyst like silver or copper. Primary and secondary alcohols give aldehydes and ketones respectively. When primary alcohol treated with copper at 573 Kelvin, it will form aldehyde. That only we have seen here. If secondary alcohol is treated with copper at 573 Kelvin, ketone will be formed. When primary alcohol is treated with catalyst like copper or silver, it will form aldehyde. If secondary alcohol is treated with catalyst, it will form ketone. Okay. Here hydrogen will be removed. Next, from hydrocarbons also, that is by ozonolysis of alkenes. Ozonolysis means addition of ozone molecule. And here for alkenes we are doing the ozonolysis. So for alkenes, ozone molecule will be added. Ozonolysis of alkenes followed by reaction with zinc dust and water gives aldehydes, ketones or a mixture of both depending upon the substitution pattern of the alkene. Here zinc dust and water will be used. Okay. Also it may give separate aldehydes or ketones or mixture of both aldehydes and ketones also. So here propene with ozone molecule, propene ozonoid will form. 3 ozone, in the ozone 3 oxygen will be there, those 3 oxygen will form a ozonoid structure with the given alkene. In the presence of zinc dust and water, it will form ethanol and methanol, and both are the aldehyde forms, so ethanol and methanol will form. Here methyl propene we have taken, which is a alkene treated with ozone. Here also ozonoid structure will form. It will form propanone and formaldehyde. Here the mixture of ketone and aldehyde may be seen. Okay, as they have told, ozone means it may give only aldehydes or only ketones or mixture of aldehyde and ketone. In the first reaction, by using propene, only aldehydes you may expect, that is ethanol and methanol. In methyl propene, when you have used, you may expect propanone and formaldehyde or methanol can be seen. Next, by hydration of alkynes. Alkynes means the hydrocarbon which is containing triple bond. By hydration means by using water. Addition of water to ethane in the presence of sulfuric acid and mercury sulfate gives acetaldehyde. All other alkynes gives ketones in this reaction. Only one ethane will give aldehyde, but other alkynes will give ketones. This is ethane having triple bond with water treating H2SO4 acid and mercuric sulfate. At 333 Kelvin it will form aldehyde. But other alkynes, as they have told, propine, when treated with water in the presence of mercury sulfate and H2SO4 at the same temperature, it will give acetone. Okay, this is a ketone, and later it will form CH3COCH3. Okay, which is a acetone. Only ethane will form aldehyde. Next to ethane, any alkyne will form ketones. Okay, this is about by hydration of alkynes, how the aldehydes and ketones will be formed. And we have seen methods of preparation of aldehydes and ketones. Both will how it can be prepared in same reaction. But now we will see preparation of aldehydes only from different methods. First, from nitriles, that method we will call it as Stephen's reduction. Reduction of nitriles with acidified stannous chloride at room temperature gives aldehyde. In the first step, imine hydroxide is obtained, which on hydrolysis with boiled water gives aldehyde. This specific type of reduction of nitriles is called Stephen's reduction. First, nitrile is treated with acidified stannous chloride plus concentrated HCl at 290 Kelvin. It will form imine hydroxide as an intermediate, and later it has to hydrolyzed with boiled water, and later it will form aldehyde with ammonium chloride. That overall reduction process we will call it as Stephen's reduction or preparation of aldehyde from nitriles group. Okay, we will take here one example. Ethane nitrile with stannous chloride and acid, acetal diamine hydrochloride will form, and when treated with boiled water, acetaldehyde will form with ammonium chloride. Alternatively, nitriles are selectively reduced by diisobutyl aluminium hydride. We will call it as dibal H, which is a good reducing agent. So, by using that, nitrile will be formed aldehyde. Okay, here we have taken one alkyl nitrile with using dibal H and water, it will form aldehyde group. We can use from esters also. Esters are also reduced to aldehydes with dibal H. Example, this is one carbonyl group treated with dibal H will give alkyl group, which is giving to aldehyde. Next, from acetyl chloride or Rosenmund reduction. What all the reductions I am going to explain from Stephen reduction, those are all named reactions and they are very much useful. Aldehydes are prepared from acid chlorides by reaction with hydrogen in the presence of palladium catalyst. Supported on barium sulfate, this reaction is called Rosenmund reduction. Acetyl chloride or acid chloride RCOCl, When treated with hydrogen in the presence of palladium catalyst and barium sulfate, aldehyde will be formed. Here if you take in the R place CH3 alkyl group, RCOCl will form in the presence of hydrogen and palladium catalyst and barium sulfate. Acetaldehyde formation can be seen. That kind of reduction we'll call it as Rosenmund reduction. Next, preparation of benzaldehyde. Itard's reaction, we'll call it as Itard's reaction. Chromyl chloride oxidizes methyl group of toluene to a chromium complex, which on hydrolysis gives benzaldehyde. This reaction is called Itard's reaction. For the benzene ring, if CH3 is there, that will call it as toluene. In the chromium chloride, it will form chromium complex. On hydrolysis, it will form benzaldehyde. When benzaldehyde is formed, that reaction will call it as Itard's reaction. Use of chromic oxide. Toluene or substituted toluene is converted to benzaldehyde. On treating with chromic oxide in acetic anhydride, the benzene diacetate can be hydrolyzed to corresponding benzaldehyde with aqueous acid. See here, benzene diacetate treated with substituted or non-substituted toluene. In the presence of chromic oxide, it will form some of the intermediate, and later on hydrolysis, it will form benzaldehyde. Next, by Gutterman-Koch reaction. This is also very important reaction. Benzene or its derivative is treated with carbon monoxide and hydrogen chloride in the presence of anhydrous aluminium chloride with traces of cuprous chloride. Benzaldehyde or substituted benzaldehyde is formed, and this reaction will call it as Gutterman-Koch reaction. Benzene treated with carbon monoxide, hydrochloric acid, anhydrous aluminium chloride and traces of cuprous chloride, it will form benzaldehyde. From benzene to benzaldehyde, this much of catalyst and some of the reagents should be used compulsorily. And this is called Gutterman-Koch reaction. These are about preparation of aldehydes, and you have seen in the same method how aldehydes and ketones have been used, but this Gutterman-Koch reaction, Itard's reaction and Stephen's reaction as well as the Rosenmund reductions are the very important reactions to produce or to form aldehydes, and for your exam purpose also. In the next session, we will discuss about preparation of ketones and physical properties, also chemical properties. We will see about these two properties of ketones. I hope you have understood completely whatever I have taught in this session. We will meet in the next session. Thank you.